my name is Thomas. As you just were told, I was here a few years ago, so it's really, really great to be back in Moscow. I really enjoyed here. And the talk I gave last time I was here was very, very deeply technical. And the talk I'm going to give today is full of a lot of details, but it's not as technical. It is meant to make sure that everybody can follow along, even if you're not familiar that much with tracing today. I work as a software engineer at Elastic. Elastic, if you don't know, is the company that makes Elasticsearch that probably a lot of you are running. And particularly, I work on the Elastic APM product. Elastic APM is a very new thing we launched recently. And I'm not here to tell you about Elastic APM. I would love to talk about it, and you can come up and speak with me later about Elastic APM, but that's not what I'm going to talk about today. Today I'm going to talk about distributed tracing. And Elastic APM is a distributed tracing solution, so you could of course use that, but you can use a lot of other open source solutions out there. Elastic APM, by the way, is also open source. Without further ado, I'll just get started. So when we're talking about distributed tracing, the first thing people usually ask is, what is tracing? Or if they don't ask what tracing is, they probably have an idea inside their head what tracing is. And there's many right answers to what tracing is, but to make sure that we're all talking about the same thing, I just wanted to go over it here. So this is what Wikipedia is saying about tracing. It says, in software engineering, tracing involves a specialized use of logging to record information about a program's execution. And then it goes on to say, this information is typically used by programmers for debugging purposes. And it's on Wikipedia, so it has to be true, right? And it's not wrong, but when I'm talking about tracing, I'm talking about it in a more specific sense than that. It's still this, but more specific. So this is just looking at what a program was doing at this point in time, and then kind of how then a program is doing something else over here, and there's some time spent in between. But in today's applications, your programs is doing a lot of different things at the same time, especially if you're using Node.js, which is an asynchronous runtime. You can be serving multiple requests at the same time. So not only is tracing this, but in the terms of what I'm going to talk about today, but tracing is also that you can see exactly how you got to a specific point, so you can follow the progress of a request throughout your entire application. So another word that I'll be using quite frequently, and I actually already used it on my first slide, is the word APM. And how many of you here know what APM means? Yeah, that's what I thought. Not that many hands. Not that many hands. So APM stands for Application Performance Monitoring, and it's basically covers a series of tools that you use to do tracing with. So you use an APM tool to do tracing. And some people might say, oh, no, it doesn't stand for Application Performance Monitoring, it stands for Application Performance Management. That's also true, but I don't want to go into the details of why there is two things that the M can stand for. It's not important right now. So let's jump into it. We have had monolith applications running in production for a long time. This goes back to the very first website. It was a big monolith application, maybe not as big, but the monolith grew bigger over time. And how did we trace the monolith? That's like the first question. Well, let's say a user comes and a user clicks a button and sends a request to our monolith application. A lot of stuff goes on inside the monolith. It makes database queries. Maybe it sends a request to a payment gateway, and it renders some templates, and does a lot of things. And when it's done, it sends a response back to the user. And how did we trace the monolith back in the day? Well, we took the data, we took the logs or something like that, and we sent them off to some data storage somewhere so we could analyze them later. That's at least a good thing to do. If you just leave the logs on the server, it can be really hard. to search them. And one of those data stores that you send the logs to, for example, that would be Elasticsearch, which is very good for searching in those logs afterwards. Yeah, so logs. Logs is one thing that you can use to trace your application, but many of you probably came to a realization at some point that logs don't give you the full picture of what goes on. It doesn't tell you necessarily what database queries is being performed in your application when it's serving a request. So a lot of people might have upgraded their tracing experience to a proper APM product. And this APM product would sit inside the same process as your application and listen in what was going on and see, oh, there was a database query and stuff like that. And that's definitely a big improvement. But nowadays, this picture is actually kind of a lie. Nowadays, you usually have a big fat front end in front of this. Or it could be a mobile app, it doesn't have to be a React application necessarily. And this is for the APM product that you installed inside your big monolith application. That's essentially a black box. You have no idea what goes on in there. So that's a problem, and distributed tracing can also help you solve that. But we'll get into that. So let's talk about microservices, because nowadays we're moving from the monolith application to microservices. This is nothing new. This has been going on for at least the last 5 years. And if you start an application, start developing a new application from scratch today, you'll probably start with a microservice architecture. So your monolith application will suddenly look like this. It will be a lot of different small independent services, maybe not necessarily all written in the same language. That could be Node.js and Go and Python and Java and all sorts of stuff in there. And when the user, and all of these, of course, still send their logs off to your place where you store your logs individually, or even you might have installed the same APM product in all of them individually, and they might all send that off to there. But then a user clicks a button in the React app, and the request comes into your router, and that propagates to another service and another service and a few other services. And you get all that information into your data store there. That's good, but you can't really see anything about how that kind of worked its way through your application. You just see each of them individually. What you really want to do, you want to be able to draw this red line and see, okay, a user clicked here, and then that happened, and this happened, and then so you can see that entire flow in your application. And that is what distributed tracing is solving for you. It's want to make a order out of the chaos, basically. So before I go any further, I should probably tell you something about agents, clients, and traces. So to be able to figure out what goes on inside your application, you need to install some kind of APM library inside the application that sits and monitors all the stuff that goes on. And some people call them APM agents. That's what we do at Elastic. We call it an APM agent. I work on the Node.js agent for Elastic APM. Some will call them APM clients, and even some will call them tracers. We're going to get into something called open tracing very shortly. And in open tracing, it's called tracers. But it's basically all the same thing. So just wanted to clear that up. So normally when you have a big microservice architecture application, the way you normally draw that is something like this. This is not a big application, but you can imagine it's much bigger than that. So you have all your essential components, and then you have arrows in between them, and you kind of see which component talks to which component, and which service talks to the MySQL database, and which talks to the payment provider, and all that stuff. That's really, really nice to see how your application fits together, but it's super, super bad to see how data flows inside your application. So no matter which APM, distributed tracing APM solution you choose today, and there's a lot of them out there, they will not draw it like this. So when you're debugging a trace and looking at how data flow through, it will instead draw it like this. So this is essentially viewing a request. This is viewing a trace coming into your application, and on the x-axis we have a timeline. So the request started at the very left, and then it ended at the very right by sending data back to whoever called it. And what happened in between the start and the end of the trace is defined by these horizontal bars, and they're called spans. And as you can see, the order service kind of have 3 spans associated with it. There is the actual HTTP request to the order service, but then there's also 2 database queries, and that's super useful. You can see that, which you couldn't see on the other diagram. And you can of course see how long each of them take. So a span have a few like very key attributes associated with it that is important to be able to draw this diagram. So of course it has a start time and it has an end time. It also have a trace ID. It needs to know which trace a given span belongs to. So if you have 2 requests to the same endpoint that travels through the same path in your application, that would generate 2 traces and double the amount of spans, right? So there'll be 1 span for each of those traces per thing that you're measuring. And besides the trace ID and the start and end time, it has a name, as you can see, so you can kind of identify what it's doing. And then a very important thing is that it has a parent ID. So each span here knows who called it. But those are essentially the basic information you need. You could argue you maybe don't even need the name, but it makes it a lot easier for humans to see what's going on. You can, of course, attach a ton of extra metadata to each of those spans to help you debug, like tags. Like you can say, okay, who was the logged-in user at the time when this request was going on, or something like that, or which host name was this service running on, and stuff like that. If you go back to this image for a second here, and then talk about that big React app there in the beginning, that's essentially, when we think about it, that is nothing but another service in your microservice architecture. It just happens to be running on hardware that you're not in control of. So it's a little bit more difficult to reason about it and trace it, but it's essentially just a service. In distributed tracing thinking, it's just a service. And you just have to apply a little bit of a different strategy of how you get data off it and stuff like that. But that's it. So let's remove some of those arrows there, and let's look at this in a little bit different way. So there is a user clicks a button in the front end, and a request comes in now. And as this is happening, each of those services are recording what goes on with using these spans. And as kind of the tree collapses and we get up again and get ready to send something back to the user, each of them individually then send off their piece of the puzzle to the APM server to your right here. And they do it completely autonomously. They don't know about the other services necessarily. They don't have to know about the other services, because if it was like the job of the last service in the line to send everything up to the APM server, it would be a lot of state to keep track of. So in distributed tracing, you don't do that. Each of them is responsible for their piece of the puzzle. And so the only thing that we then have to do is, remember, we needed to know the trace ID, and we needed to know the parent ID of this every time we create a new span. So of course we need to send some data down, but not too much. And that brings us to the first challenge of today. So inter-service communication. How can services communicate today? Well, the most popular, of course, is HTTP. But you can also have a binary protocol. You can have Apache Kafka, very popular as well, or some kind of message queue where a job is put on the queue, and then maybe a minute later, another service picks it up. We need to be able to track all these. This is not a full list. There's a lot of other ways the services can communicate. But today we're just going to look at HTTP because everybody knows how that works. It's simple, but essentially, more or less, it's the same for the other ways. How do you normally send metadata along an HTTP request? Well, we have these nice HTTP headers. We can use those. And essentially, that's what all APM distributed tracing tools they do. They use the headers. They simply inject a magic header, and so that the outgoing service injects every time there is a request out. It injects a header, and then when you get a request in, you just look for this header. And that's how it works. Very simple. And let's look at how one of these headers might look. So this is a header called trace parent. Trace parent is actually a standard, or it's becoming a standard. It's made by W3C in the trace context working group. But it's currently still draft, so things might still change, but I'm going to use it here as an example because basically, if we don't get this type of header, if you have a big microservice architecture setup, and you have two different APM vendors that you're measuring something over here and you're measuring something over here, if they're sending requests to each other, they can't continue the trace because they're all using their own proprietary headers, so that will not work. So we need some kind of standardization to be able to draw that line, even though we're using multiple vendors, and that's what this working group is working towards. So you don't necessarily need to know what the value here is, but I'm just going to go over it anyway because it kind of gives you a nice idea of how things work behind the scenes and what's important and what is possible. So first there is a version, 1 byte, that just essentially allows us to make a new version of the header and not breaking things. But then here's the important part. There's a trace ID, which is at 128-bit random number. And that is 128 bits is enough to be globally unique. So the first service that gets a request where there is no header already, say, oh, I'm the first. Well, I'll generate this 128-bit trace ID, and then it's just going to pass it on to the other services, and they'll just reuse that ID. And then there is the parent span ID. Remember, you needed to know who your parent was. So that's a 64-bit random number. That doesn't have to be globally unique because it just has to be unique, of course, within the trace ID. And then finally, there is 8 flags we can set. And currently, there's only one flag in use. That is the recorded flag. The other 7 flags are there for future development if we ever need it. So that's nice. The recorded flag basically means that the service that sent this request and added this header to the outgoing request, it decided to record this trace. And record means basically sampling. So when you're tracing your application, when you're instrumenting your big application, if there's hundreds of requests per second or something like that, or even more, that's a lot of data. So you probably don't want to sample everything. So you maybe only want to sample 5% or 1% or something like that. And this signals to the ongoing service if we decided to sample or not. There's no rule that the next service in line have to follow this flag, but it depends on your sampling strategy. You can, of course, choose a sampling strategy that makes sense for you. So another problem is, I touched upon this briefly, like if you have 2 different vendors APM vendors in the same environment, let's say we have 3 services, A, B, and C, and in the left one here, we are using this fictitious APM vendor that I made up called Congo. We're also using that in service C, but it's communicating through service B, which that department, they're using this other one called Rojo, and we can't really convince them to switch to Congo. So how do we make sure that when we get over to Congo, if we want to have any information that we want to know what goes on in Congo when we get to the second one that's instrumented with Congo, but maybe it's lost when it goes through that Rojo one. And the way we deal with that is another header that is also part of the trace context working group, and it's called trace state. And the idea of that is to solve this specific problem. And of course, it's also a draft because it's part of the same working group proposal. And you can see here, it's basically a comma-separated list of key value pairs. And each APM vendor gets their own vendor name and can put any value they want in there. There can only be one. You can only be there once. I mean, your key has to be unique. But that allows Congo to add a Congo key in the beginning and add some kind of ID or something that it needs to communicate to the next one. And the first one in the list, the most left one, will always be the most recent service. And then every time a service forwards this header to the next one, it adds itself in the beginning, and then everything moves one over. And if it's already there in the list, it removes itself from the list and adds itself up to the front. And there could be up to 32 unique vendors. So good luck having a setup where you have 32 unique tracing vendors in the same infrastructure. So that solves that. If of course they all follow the standard, but I've talked to basically all the vendors that do distributed tracing, and they're all super excited about this because it solves a lot of headaches and everybody wins. So everybody is actually on board, as far as I know, to adopt this once that it becomes a proper standard. So the future looks very, very bright when it comes to this. So another problem that you might already have thought about if you were paying attention before is, well, when we have a browser, like a React application that we are running in the browser, we have a kind of chicken and hen problem. We have a problem where the first request that the browser makes is just the user typing in the URL or clicking on a link on another web page. So the browser is not running our agent. So the browser can't start a span because there's no code running in the browser yet. So how do we solve that? Well, a request comes in from the client. The server sees, oh, I'm the first one to be called, so let's generate a trace ID. Since this is what I do always, I will start a span as well to measure this incoming request. That's all good. But then it will say, oh, I'm actually sending down like the template to the client. This is like the first time the client gets this data, this HTML page. So let's just pretend that I'm the client for a moment. Let's generate a span ID on behalf of the client, and then just make sure that the parent for the span we just started, that's set to point to that span. That span ID that we generated for the client. So it's actually pointing to a span that's actually not there yet. And then we render the HTML template and we send it back to the client and end the server span. And so the client get an HTML page back, and that includes all the initialization logic for the APM agent. So this is how that looks in Elastic APM. Say you have a simple template here to bootstrap your system, and you load the APM agent, and then you have this initialization logic. And in our case, but this is basically the same. Everybody who does this, we have three arguments, three options here: page load trace ID, page load span ID, and page load sample. We just say that if we decided to sample this or not, and then this code loads, and it's like, oh, I'm being told to actually create a span for something that already happened, and it says, oh, but wait a second, I already got this template. Actually this span started a while ago, and how do we know when to kind of, we need to give it like the right start and end time, right? Luckily there is as you probably know, there's the navigation timing API in the browser, and we can use that. It has a lot of nice events. We can see when the request was actually started, even though we were not running at the time. And it has a ton of events. The one we're interested in is fetch start. It tells us when the request was made, and therefore using that we can set the exact start time. So that's super nice, and we've solved that problem as well. So far so good. We're solving a lot of problems. But there was another problem that I briefly also talked about before, which is this is in our genes as developers. We want to see everything. We want to know exactly what's going on. So it's very, very easy to fall into this trap and just collect all the data. And I'm just here to tell you a simple message: don't be this guy, because you will pay for it at the end with a lot of storage space, because just running a decent-sized application in production can generate gigabytes of data, of tracing data. One solution is, of course, oh well, let's just delete everything that's 1 day old or something. But that's not fun. You need to be able to see trends moving over time. So it's not nice to delete data. So we want to be able to keep it as long as possible. So of course we use sampling. And the most simple form of sampling is head-based sampling. Head-based sampling basically means that it's the first service in the chain of services that decides, do we want to collect this data or not? Do we maybe roll the dice, like a random, like 1%, 1 out of 100 requests, we're gonna sample that. But there's a lot of other more advanced sampling techniques that has pros and cons. I'm not going to go into that now. Another big problem that especially we have in the Node community is asynchronous, an asynchronous runtime. So Node is born asynchronous, which is super nice. But it also comes with a few problems, especially when we're talking about knowing exactly what's going on inside the application at any given time. How do you know when a function is running, like which requests cause this function to run? Well, one way is to carry a reference to the request all over the place. That is tedious. It's possible, but it's very, very tedious, sometimes almost impossible. So you often need some kind of continuous local storage or something like that to solve this problem. And a lot of APM agents that are built for Node, they solve this problem for you, so you don't have to. That's Elastic APM does that, so you don't have to always keep in mind, which is the active span, so when I start a new span, I should point to that as the parent. The agent takes care of that for you. But you can, of course, choose to manually do that if you want, but it's something to keep in mind. And this is not as big of a problem in Python and Java because by default people are not doing asynchronous programming there. There's a lot of nice asynchronous frameworks out there for Python and Java, etc. But it's not something that people usually do. But in Node, it's a big problem. So that concludes all the nasty problems that we have to deal with as when we deploy distributed tracing. So there's a few standards out there already to help us not reinvent the wheel. One of them I already talked about, developed by W3C, so I'm not going to go into more detail about that. But the other really big elephant in the room is open tracing. How many of you have heard of open tracing? Just about as many people who have heard about APM. I wonder if that's a coincidence. So open tracing has been around for a while. It's not as big in the Node community as it is in other communities, or in the JavaScript community as it is in other communities. And I think one of the reasons for this is this asynchronous problem that I talked about before, because it's super, super hard to keep track of these things. And open tracing, the open tracing standard doesn't try to solve that. It's outside the scope of the open tracing standard to solve that asynchronicity problem. But it is out there, and it does have some benefits that are interesting. So at its core, open tracing is just basically a set of APIs that you as a developer, when you are saying, oh, I want to measure this piece of code over here, let's start a span here, and let's end the span down here after we've done running that code. That API that you're calling you're calling that on a tracer, and you're calling start span, and you're giving it an argument. Like the first argument is like the name, and then there's an options object that's a second argument, and then that returns a span object, and you know that you can later call finish on that span object to say that you're done measuring. And that whole API is defined by open tracing. That means that the most obvious thing that means is, of course, that it's vendor neutral. So you can switch from one distributed tracing vendor to another as long as they support open tracing. Though in my experience, that is not the biggest benefit. Because it's not that hard to switch, to be honest. But it's there. It's there if you want it. No, the biggest benefit is that we as APM vendors, we've had to for years we've had to like figure out how to instrument your application, and it meant that you're using Oracle as your data store, as your database. Well, we have to then take the Oracle driver and look inside the Oracle driver and figure out if there's some hooks we can use to know whenever you make a query to start a span on your behalf. So you don't, it would be kind of tedious that every time you had made a query anywhere in your application, you have to remember, let's start a span, let's end a span. That doesn't scale. So we as APM vendors, we've usually, what we've done is we've hooked into each of the database drivers, and so we get notified every time a query starts and finishes. And that's very nice, but usually there's no hooks we can use. So we have to do some nasty things with monkey patching and things that is too scary to talk about here. So open tracing solves this by if you are a database, if you're a developer of a database driver for Node, for example, I'm just using a database as an example, but anything that you want to trace, you can accept an open tracing tracer as an argument, an optional argument. And because you, as the developer of the driver, you know exactly when a query starts and when it ends. So you can be open tracing compatible. That is the biggest benefit. If we get more and more of these vendors to become open tracing compatible. So how does the API look? Well, we require open tracing, and we start a new tracer, and then we start a span, and then we do some work, and then we finish the span. That's simple, right? That is the most basic approach. We can also augment the span with some extra metadata. So open tracing have the concept of tags, which is a tag you put on the span. Like for example, you say, oh, which was the user who was logged in when this span was recorded? We can record that. We can also record what's called logs, which is like moment in time events that has a specific timestamp. So it could be an error, for example. So we associate an error happened here while this span was going on. We of course also need to be able to tell how spans relate to each other, so you can make children of parent spans. And there's two types of children in open tracing. There is there's a child of and there's a follows from. Child of is usually if the parent expects a result at some point, and follows from is just we're just starting some work, but we don't really care about the result. And then also we need, of course, to be able to inject this magic header or this other thing into an outgoing request, and we need to, so there's ways to do that. So you have this, you take the context of the span, and you say, oh, this is, we want to inject it into an HTTP kind of format, and we give it just a blank object, and then it will populate that blank object with the headers that it needs, and then we can just ourselves apply those to the headers of the outgoing request. The same goes the other way. Of course, we can read the headers and make sure to then start a span with the context of the span that was on the other service. And currently, open tracing have like 3 standard formats of how you can work with these headers. If you can, work with inject and extract. There is HTTP headers, which we saw, but you can also just have a pure textual representation. So if you have something where it's not an HTTP request, but you can still have something in text, you can use the first one. But if it's a binary protocol, you're sending data over, you can use the last one there. But then, of course, all the examples you saw before was just a generic tracer. That's a no-op tracer. It's actually, you can npm install open tracing, but it doesn't do anything because it doesn't know where to send the data. So we, as an APM vendor, we have the ability to inherit from that tracer and make a custom tracer that you as users can use. And we are free to define any kind of config options that we want that tracer to have. So this is config options that are relevant to Elastic APM. We need to know where the APM server is, so we give it a server URL and stuff like that. And then we can actually, using open tracing, we can initialize a global tracer, and then at any time later in your application where you need access to your tracer, you can just get the tracer anywhere in your application, and it gets access to this tracer that we started on when we started up the application. And by the way, this is a work in progress, I have to say. This might still, the API for how this works in Elastic APM might change. But it's work in progress. This is just an example of, for example, how you would. There's a lot of modules out there that help you create these spans, so you don't have to do it automatically. For example, if you're using Express, there is an Express open tracing middleware that you can use, and just give it the tracer and add it as a middleware, and then every time a request comes in, it will automatically start a span, and when the request ends, it will end the span for you. And this is similar to how we would do it with a database driver, for example. Yeah, you can see, just give it the tracer as an argument. Super simple. So how do you get all this stuff into production? I just prepared like a little checklist that is probably nice to think about when you're thinking about deploying open tracing. So you need to, of course, think about if the vendor that you choose, if it supports all the languages that you're using in production, because otherwise you will not be able to see into one of these unless you do some manual lifting. You need to know if you're using serverless. Serverless is a little bit different in how, when it comes to APM, so you need to make sure that the APM vendor supports serverless infrastructures, if that's important to you, of course. And of course, does it support the databases we're using? I mean, if it doesn't, you can always, as you saw before, you can start and end the span manually, but it would be nice if it like automatically did it out of the box, or if that database driver that you're using supports open tracing. So check that. And does it support the inner service transport that we're using? Just because that we can of course use the inject extract we saw before, but it would be nice if we didn't have to do that every time we made an outgoing HTTP request. So it would be nice if the agent that we use just did that for us automatically, because otherwise we're going to add a lot of logic in our code that's not nice. And finally, is it real user monitoring? This is when you instrument the client, like the React application. Does the APM vendor that we choose, does it have an agent that supports the environment that we are running our client in, if that's important to us? Real user monitoring might not be important for everybody, but for some people it's super important. And so if you can't answer yes to all of these questions, you have to check, of course, that, and not everybody supports everything, you have to just check that the vendor that you choose allows you to easily extend the agent or manually create spans in the way that you want, or manually serialize and deserialize data. And of course, if it's supporting open tracing, then you know there is a certain set of minimum things that it supports, so that's super good. Some bonus questions that I think actually is kind of important is, can we, when we collect all this data, is it then stored in some proprietary data warehouse somewhere where we can maybe view the data, but we can't actually access the data? Or do we actually get access to the raw data? Can we host it ourselves? Can we run this on-prem, or do we have to put it in the cloud? Or this I think is very important. And equally important is, can we correlate this data that we are collecting with our other data? Because we're probably already collecting logs or metrics. It's nice to be able to see those things together. When you're just getting started, don't try to instrument everything in the beginning. If you already have an existing big infrastructure, just instrument the things that are important first. And if you are in the process currently of breaking up a big monolith application, it's a good idea to see if you can get instrumentation into the monolith first, and then kind of make it a rule, just as we have rules about every time we might write a new piece of code, we make unit tests. We all do that today, hopefully. But it would be nice if we say, okay, every time we deploy a new service, we take a service out of the monolith and deploy it separately, we add tracing to it. If we can make that a habit in our organization, we save ourselves a lot of hassle down the line. Which leads me to all the data that we are collecting, and how that data might be useful together with all the other data that we are collecting as well, because we're already collecting logs, we're already collecting other things. And I feel like there's 4 things, 3.5 maybe, that we all collect or should collect. The first is, of course, logs. We've probably all done that from the very beginning. That's no news. But once you've done that for a while, you graduate, and then you start to collect metrics like CPU, performance, memory usage. Maybe in Node.js, you look at the event loop saturation or stuff like that. And you graph that over time. That's super nice. But it would be nice if we could correlate CPU usage to the response times, for example, and stuff like that. You might also have installed a custom error logger to get like rich, detailed error logs. If we can go directly from the error to the trace, that would be super, super nice. So we can just view the errors, like, oh, this is what happened, stack trace, blah, blah. Click a button to view the trace, and then suddenly we can see how we got to that point in time. And then, of course, finally, the traces. So yeah, that's hopefully by the at some point in the near future, that's all the data you're collecting. And what you want to focus on is trying to see if we can find a provider that can connect all this data together. So we can go from one to the other, and if you're viewing the logs, let's view the trace for this log. So if you're viewing the trace, let's look at the logs that was generated when this trace happened, et cetera, et cetera, et cetera. So the few more minutes I have left, I just want to show you some things here. We need to make this a little bit bigger. So I'm not going to live code this because we don't have time for all the mistakes I'll make. But let's say we have a service, simple service. This is just an example, right? Make this a little bit bigger. And it's just a web server that responds with hello, Holo.js, right? So if you want to use open tracing to instrument this, we should start by requiring the tracer here. We should configure the tracer. We started with a service name A. In this case, just for the sake of the demo, I'm going to disable automatic instrumentation just to kind of show how you would do this manually. And I'm going to disable trying to capture any errors that might happen, just to get it super bare bones. And then down here, when the request comes in, we are starting a span. I'm just giving it the name of the HTTP method and the URL. And then we set up a listener for the response. When it finishes, we also finish the span. But other than that, it's the same app. Let's try to run this, and let's try to curl localhost 3001 hello. So I already set this up to with an APM server and Elastic APM and everything. So it's now recording data. Did I start the server? Let's see. Yes, the server is running here. So the server is just running locally, and I am. Let's collapse this. So I'm running Kibana and Elasticsearch here on Elastic Cloud, so I don't have to run it on my laptop. So if we reload this page here, let's hope the internet is working. Otherwise, we'll just do like this instead. So if I had to be running everything here while I was running Keynote with this amount of memory that I have in my machine, it would completely drain all the power and everything would not work. So let's see if it's probably just internet. Luckily, I have my phone with me. So we'll just see. Failed to connect to Nokia 9000. Maybe I should get a newer phone. There was that one. Great. That's a much better idea. Nice. You all are so helpful. It's great. This is so I did the one thing that or I forgot to do a very important thing when I started. I didn't slaughter any demo goats to the demo gods. So yeah, turn it on. That's probably a good idea. Let's turn the Wi-Fi off and then turn it on, and then. Hooray! It's actually let's try my. I'm just going to try my own phone again because this whole OGS thing. That's fantastic. Okay, we're going to try this phone instead. It's the Alex one. Oh, okay. Now I'm not going to touch anything now. It seems to be working now, even though I'm on the Radisson guest Wi-Fi. So it got the service, service A, and we can click on it here, and we can see there was some requests to get hello, and we can see there was, in this case, there was only 3 requests, so it shows up here as 3 requests, and we can see here that there is one span, the get hello span that we created. So it's actually not that interesting. So let's try to instead say, let's skip this. Let's go directly to make another service. Let's make another service. We make another service here called service B, and it looks very much like the one we just had. Except it says hello from service B down here. And so let's start service B, node, service B, like this. And then we have service A here, which is just going to send a request. So it's just going to act as a proxy. So this will basically just proxy the request from we sent to it to the other service, just to kind of show that we have 2 services and they're communicating with each other. But actually, before we do that, we have to do one other thing because we're not passing over the header, the special header. So actually, I should look here. There we go. So here we're using this. We create this empty object, and then we use the tracer.inject and say this is HTTP headers. We give it that empty object, and then because we don't have any other headers that we care about here, we just add it to the options to the request, and we send off the request. So let's run that. There we go. And actually, let's just make sure that we should actually use this one here. So here this is a service B that is receiving the request, and we are extracting the context from the headers, and then when we are starting the span, we are saying make this span a child of this other span that we got from the headers. Okay, so let's run that, and let's call hello2. And now you can see the result is hello from service B, even though we were calling service A, but it proxies through. And let's actually just try to hammer this with a lot of requests. Let's call that service hello3. So now we're just sending a ton of requests to it just to kind of simulate how we'll look. And done. So that was a lot of requests, 940 requests. And if we go over here and go to traces here, and then fingers crossed, I'm going to reload. There we go. So let's look at traces. We have three traces here. Let's look at the last one here. And as you can see here, we have a lot of requests coming in. And currently it looks kind of uniform because I was just randomly giving some delays to each request, so it looks very uniform. But normally you would see like the first, you have a lot of requests all the way to the left up here that are served super fast, and you have this nice long tail of some really slow requests down here. But if we go down here in the bottom, we can actually see service A here, get hello 3, and then service B, get hello 3 as well. And we can even click on this, and we can view details about this. We can see which system it's running on. We can see, this is not doing very well with, let's see if, that's better. So we can see information about if a user was logged in, we would be able to see that. If we had added any tags, we would be able to see that. And we could even add HTTP headers, so we could see the HTTP headers of the incoming requests. And yeah, so that's a very quick demo with a little bit of trouble, but we got that sorted out. So if you want to get more information, if you want to learn more about OpenTracing, you go to opentracing.io. And if you want to learn more about Elastic APM, you go to elastic.co/solutions/APM. And of course, you can always reach out to me on Twitter. My DMs are open. If you want to know anything about Node, of course, or OpenTracing, or the new standard for these headers, or Elastic APM. And if you get so excited, if I really got you interested in this, and if you want to actually get involved, that's also possible because this is open source after all. So it's hosted on GitHub. And the easiest way to find out what that's about is going to GitHub Elastic APM. There's a different repositories for each agent, so the Node agent is linked from that central repository if you're interested in the Node agent. And all the demos I did now are using Elastic APM and using OpenTracing. That is currently work in progress, as I said before, so there's a PR open here, and if you're interested in this, I really would like your feedback so we can make sure this is the best OpenTracing agent possible. So all feedback is highly appreciated. And with that, spasiba.
Thank you, Thomas. We have time to questions.
Hi. Thank you for the talk and for your math skill set, Max. But what do you think about generation of trace ID on the client?
Generation of
trace
what?
ID, like the parent ID on the client. Yeah, like I don't have any server in the first place. So I need to generate the ID on the client in the browser.
So it's because you're serving a static HTML page, I imagine?
Yep.
Yes. That's a very good question. It's so there is ways to generate to get randomness in the client. You will of course have to wait until, well. No, that's still possible. You would have to make a script that would then, when the first time it's loaded, it generates this automatically. Getting randomness in the browser is not necessarily that good, the randomness you get out of a browser, because not all browsers have access to newer randomness APIs, so you have to resort to something like MathRandom, which is not that good to generate randomness. But it's definitely possible, especially if you're running on newer browsers. Then it should be possible. But you have to make this random generator by yourself. It would probably make sense if we built that into Elastic APM in a way that you could kind of seed your own first span. Yeah. That's thanks for asking that. it is possible, but with a little bit of trickery, and we should make that even easier.
Any questions? Oh. Hello, my name is Artyom. Thanks a lot for your talk. So the package, the NPM package that you just talked about, it's only supported by Elastic Storage. There is no other option.
Yes, common for all the tracing the distributed tracing vendors out there and open tracing vendors is that they all send their data off to their own backend. There is currently no easy way of sharing data between different vendors when it's stored. We use Elasticsearch for our so I didn't show that, but all the data here that we saw in the UI for Elastic APM, it's down in Elasticsearch. So you can view all the data; it's there in your indexes.
So you can intercept it and read it and.
Yes, and you could even the API is public. Like public in the sense that we have shared how it looks, so you can even make your own agent and send data up to Elasticsearch. Actually, we have a server that's called the APM server that's the one you're communicating with, and then that takes care of storing it inside Elasticsearch. It does a little bit of validation of the data, but you basically send data to that server, and then that stores it in Elasticsearch. If that answers your question. Ish.
And I just can I ask you a second question?
Yeah.
I just had some experience, and I should say a bad experience. Okay, you just showed on some slides that it has some binding to Express, like a middleware. So obviously it should send or end a span on request and event, doesn't it? Yeah, somewhere you showed that it connects to Express abuse or something.
There.
Yes. So obviously it calls span end and sends all the data on request.
It does that for you.
Or request end, but I experienced a lot of troubles. I mean, basically I use the same approach all the time, but sometimes, for example, you have an infinity loop, or you have some application developer code. It's just bad, and what to do? You will never see the. I mean, it will never be called.
That's a good point. So there's a lot of edge cases, and we try in Elastic APM to take care of all those edge cases for you, so you don't have to think about that. But we technically don't know when a span ends. It could be like you had a span that goes on for 5 minutes or an hour, technically. What would normally happen in a situation like that is that at some point the HTTP request would time out. So the incoming HTTP request would time out, and we actually have a feature in the agent to detect when that happens. So when it times out and you haven't ended the span, then we can actually generate an error, and you can see exactly where it timed out. So it will actually give you a stack trace to where in your code you have a problem. That's a way we try to deal with that problem. It's a complicated problem to solve because it's hard to look from the outside and see that it's not on purpose. But we try to do it by generating these errors when we detect it. But that is not something Open Tracing is trying to solve. That is something that each vendor tries to solve in their own way. That's how we try to solve it.